In our previous video we looked at the force on a single object in isolation, and we had Henry crashing and we looked at the forces involved in that. Today we're going to look at an entire system and relate it to Newton's third law, one of the most misinterpreted in the whole of physics. So instead of looking at one object, we'll look at two objects and the interactions between them. So we'll look at the example here of Duck maybe doing some shunting. Now what will happen is, as Duck moves along, he encounters a stationary truck and applies a force to it as he shunts it, which then moves the truck forward and causes a change in momentum for the truck. Now what we can do is consider how Newton's third law applies to this. Okay, as Duck came in, he moved the truck by applying a force. So that force was F, okay, and it caused a change in momentum, delta P, over time. An equation we should now be familiar with. Now, due to Newton's third law, that means that Duck, having applied a force F to the truck, experienced an equal and opposite force. So, minus F applied to Duck. It happened for the same period of time, t. The force was the same, it happened over the same period of time for both objects, and that means that Duck must have experienced exactly the same change in momentum, delta P, but just in the opposite direction. So both objects experienced the same force, but in opposite directions, which means that both objects experience the same change in momentum. Now, if we look at that, that means that the truck experienced delta P, Duck experienced minus delta P. Overall, there is no change in momentum. Each individual object experiences its own change in momentum, but for the system as a whole, due to Newton's third law, the truck went plus delta P, Duck went minus delta P. Overall, there's no change in momentum. And that means that providing no external forces act, which we haven't got in this situation, momentum is always conserved. Now, problems that deal with conservation of momentum are very, very common sort of exam-based questions. And simply they might ask what happens when what happens to the speed of objects when they interact. You don't now need to go through Newton's third law and the force calculations we've just shown in that much detail. To do that, we can shortcut simply by knowing total momentum before and recognizing that that must equal the total momentum afterwards. Simply because momentum must be conserved, so we must have the same total momentum before as afterwards. Problems like this become much clearer with a worked example. So we'll have a look at a worked example of this, where we have a truck of mass, say 2,000 kilograms, which was originally stationary, shunted by Duck with a mass of, let's say, 8,000 kilograms and a speed of perhaps just 2 meters per second, coming in nice and slowly. Okay, and to work out, let's say, the join together and move off together after the collision, and we'll work out the speed that they then move off at. So we know that before the collision, the momentum of the truck is 0, and the momentum of Duck is 8,000 times 2, which is 16,000 kilogram meters per second. And without doing any calculations, we know that afterwards the momentum is still 16,000 kilogram meters per second because it's conserved. But we now know that the mass after the collision is not 8,000 or 2,000, it's those two combined. So the mass afterwards becomes 10,000 kilograms, which means that the new velocity will be 1.6 meters per second. 16,000 momentum divided by the mass of 10,000 gives us a velocity of 1.6 meters per second. It's quite interesting now to consider what's happened to the kinetic energy in this collision. Momentum has been completely conserved, as we'd expect from Newton's third law. If we look at the kinetic energy, well, before the collision, the kinetic energy of the truck was 0 because it wasn't moving. The kinetic energy of Duck by half mv squared, so half times 8,000 times by 2 squared, gives us 16,000 joules. So before, kinetic energy, 16,000 joules. After, same equation, half mv squared. So we've got a half times the mass, which is now 10,000, times by the velocity squared, that's 1.6 squared. When we run the numbers of that, we find that we've got a kinetic energy of 12,800 joules. And we've actually lost some kinetic energy in the collision. Now, if you think about it, of course you would. You'd expect a collision like this to make some sound, and there'd be some heat involved. So the little bit of excess that we've lost there, that 3,200 joules, has been lost as sound and heat due to friction and things like that. But that means kinetic energy is not conserved. Energy overall is, momentum overall is, but kinetic energy is not conserved. And therefore we describe this collision as inelastic. So an inelastic collision, kinetic energy is not conserved. Okay, a couple of special cases now that we'll look at what happens when the objects happen to be very similar, or in fact in this case identical masses. Okay, So most collisions are in fact inelastic. We do lose some kinetic energy despite momentum and overall energy being conserved. There are occasions though where you do get elastic collisions, and in scenarios where things are of equal mass, quite often that's an assumption you can make, is that collisions are nearly elastic, which is something we'll look at in thermal physics later on. So if we look at a case here where we've got two objects of the same similar mass, okay, so we've got Bill and Ben, twin engines. Now we'll have Ben as stationary, so that's 0 meters per second, and we'll say the mass here is 6,000 kilograms. Okay, and on the other side we've got Bill, who we'll say is moving at 10 meters per second, and also has a mass of 6,000 kilograms. Okay, and we're going to look at a scenario here where they do not join together. Okay, so Bill comes in, collides with Ben, and Ben then moves off, Bill having transferred all his energy to Ben. Okay, so before the collision, the momentum of Ben is 0, and the momentum of Bill is 60,000. Now, if after the collision Bill comes to rest, Bill will be then completely stationary. So this is before. So after, Bill will have 0 momentum, which means Ben has got it all. He's got the 60,000. And then because he's an equal mass, his velocity will have gone to 10 meters per second, whereas Bill's is 0. And if you run the numbers there, clearly you've got the same numbers. So Bill before the kinetic energy, we have the same numbers as Ben's afterwards. So the kinetic energy here is conserved. So if kinetic energy is conserved, we have what's known as an elastic collision. Sticking with Bill and Ben, so same mass for both of them, 6,000 kilograms again. Okay, what happens if they're actually moving towards each other at the same speed? So let's say 5 meters per second for Ben that way, 5 meters per second for Bill that way. And let's consider what's happening here. So we've got an initial momentum for Ben of 5 times 6,000, which is 30,000 kilogram meters per second. But for Bill, we've got minus 5 as he's moving in the opposite direction, times by the 6,000, which is equal to minus 30,000 kilogram meters per second. Now that means the overall total momentum is 30,000 add minus 30,000, which is 0. So as these two objects move together, what should happen when they collide is in total they'll have 0 kilogram meters per second. So what will happen is after the collision, the velocity of both objects will in theory drop to 0. And that is a completely inelastic collision. A last sort of worked example scenario to sort of consider is, well, what happens if things don't collide with each other, but actually they move apart because a force forces them apart? So here looks like two good things to mix together. A fuel truck that we'll just make up a mass for, and so that's 2,000 kilograms. And our gunpowder truck, a little bit smaller, so we'll say that's got a mass of 1,000 kilograms. Okay, and what we're going to do is there's some kind of explosion and they move apart. Okay, so in this scenario, before, momentum is 0. Now, to work out what the speed of one of them is afterwards, we'll need to know the speed of the other one afterwards, or more correctly, velocity, because it's actually, they're going to move in opposite directions, so the direction factor here is going to be all important. So let's say we know, somehow we know that the gunpowder truck moves to the right with a velocity of 10 meters per second. We know that momentum after still has to be 0, because it was 0 before when they were stationary, before the explosion. We know that the gunpowder truck, however, has a momentum itself afterwards of 1,000, that's its mass, times by 10, which is 10,000 kilogram meters per second. That means that the fuel truck, in order to have a total momentum of 0, must have minus 10,000. Knowing that its mass is 2,000, we can find that its velocity is minus 10,000 divided by 2,000, which is minus 5 meters per second. So quite simple. It's the same methodology as when we looked at the collisions, but it's just thinking of things in the opposite direction.